My name is David Hamilton Nichols. I'm a fellow of the Royal Society of Arts. I'm a speaker, author, investor, and producer, and I will be your MC for the next three panels. We're excited to kick off our fireside chat on space debris removal. Joining me on this chat are Scott Amyx, managing partner of Astor Perkins, and Luc Piguet, CEO of ClearSpace.
Thank you. Thank you for having me.
All right. Welcome, Luc. So we'll give you several minutes for your presentation, and then we'll go ahead and transition to Q&A.
Okay, fantastic. So I'll check if I can maybe share a couple of slides just to give an overview of where we are, what we do, and where we're going. Just give me a minute if I manage to get around my screens too. I hope that works. There we go. Can you see my screen?
Yes.
Yes, good, fantastic. So ClearSpace is a spin-off from the EPFL in Lausanne. It's a Swiss Institute of Technology. It's our little MIT Swiss size. We founded the company in 2018, initially really to remove debris. And what drove us essentially was issue we had on a CubeSat we launched in 2009 into the field of the debris of the Cosmos-Iridium collision. Once we got started in our venture, we realized that debris removal is just one use case of in-orbit servicing. And the problem essentially comes back to the fact that the space industry doesn't have servicing capability. The road transportation industry has, the shipping industry has servicing and maintenance capabilities, the aviation industry does, but the space industry doesn't. And essentially, we realized that there's a lot of other use cases for the same stack of technologies. But we built on quite some research done and worked on capturing object in space and then navigating a stack, essentially. What drove us as well is the fact that the space environment is changing rapidly. As you can see in this animation made by the European Space Agency, it's already quite crowded. Obviously, every single dot is really big compared to the real object in space. They're drawn like this to give a feel of the size and understand where they are. Otherwise, we wouldn't see them that much on this animation. But it gives you an idea that this is a rapidly evolving environment. And at the same time, the capacity to reach orbit is increasing rapidly. So essentially, it's an industry that needs servicing, right? And that there's a lot of objects in space already. The side effect of not having servicing in an industry like this is the number of abandoned objects, satellites, and rocket bodies in orbit. And before Starlink, for the last 20 years, on average, we added 74 new derelicts in this environment. So if we wanted just to keep the environment stable, we would have to remove at least 74 objects per year to keep the environment stable as it is. Today, ClearSpace is already working on 3 different missions, right? We have the ClearSpace 1 mission. We won a major contract with the European Space Agency for about 100 million euros. We won the tender in 2019, but then secured a contract and kicked off operations in 2020. We are also working with the UK Space Agency on a second mission where the objective is to remove 2 objects from orbit and then refuel the servicer. So going already to a reusable platform in orbit. This is a mission where we are in the phase B today in competition with Astroscale. We expect the tender for the complete mission to come out somewhere early next year. We think we're in a good position to secure the second mission, and we have the right set of competences on board. The third exercise we work on is not space debris removal, but life extension of a geostationary satellite, using essentially the same stack of technologies. That's a mission we work on with Intelsat. So we have already term sheets signed with Intelsat on the service conditions. We're negotiating a contract with them and submitting the final proposal to the European Space Agency for the development part of this mission, which would be funded partly by European member states in terms of development cost, and with a lead from Luxembourg. Right at this stage, we are in a very good position as well because we have confirmed support from different member states across Europe. Now it's really a question of putting a viable proposal on the table. Selection will be this summer. And that's a 150 million contract where there's going to be a co-funding of about 20% out of ClearSpace inside funding. So the roadmap for us looks like this. We have this first ClearSpace 1 mission that is planned to fly in 2026. Then we have the Clear mission, the ClearSpace 2 mission, if you want, with the UK Space Agency, where we remove 2 objects, which will likely fly somewhere in 2027. and the third mission, which is the life extension and VO, all using the same stack of technology of Rendezvous, some adjustment on the way we do the capture, but essentially a very common baseline of technologies to be able to provide different types of services in orbit. And this is planned to fly in 2027, start service in 28. So this is the roadmap we have on the table. Today, ClearSpace is about 100 employees across, mostly across Europe. We just set up our entity in the US. We incorporated ClearSpace today, Inc. in the US 2 weeks ago. And the team is growing. So we have already 25 people in the UK. Luxembourg is going to grow rapidly. We're a Luxembourg holding company. So we have the holding of the complete group is incorporated in Luxembourg. But then we have an entity in Germany, our main entity in Switzerland, and then the US, which is building up. It is essentially a very diverse and experienced team coming from either agencies, operators, prime integrators. Most of our team have flown multiple missions, so a substantial level of experience. So that's the other element I just wanted to rapidly share with you is the way we go about for funding. At this stage, we already secured on the contract close to 135 million euros, and we raised about 31 million, actually here it's written dollars, it should be euros, 31 million euros of equity funding. So most of our funding comes from missions and sponsorship, right? Missions, some grants, some sponsorship. If we're successful this summer, we will add a 40 million additional contribution to this total amount, which would bring us to a position where we can essentially present a leverage for investors, which is a 1 to 5 kind of leverage at this stage. That's what we try to target, but essentially also provides us beyond that support and knowledge transfer from agencies into our team. It's a relatively complex type of mission, what we do. It's not easy to implement. And for us, it was just the right natural way forward to maximize as much as possible non-dilutive funding. So that's what I wanted to share with you rapidly about where we are today. We are looking into, so we closed the Series A end of last year. We're looking into a prime right now to do maybe an extension of Series A to give some more freedom because we know exactly what we need to develop. And we had to reduce a little the ambition that we had based on the funding. So we're looking into a Series A prime and expect to do a Series B somewhere in 2024.
All right, great. Thank you, Luc.
That's about ClearSpace.
Thank you for that overview. I appreciate it. Now, most I think would agree that the problem that you're trying to solve is a very real challenge. However, there is also, let's call it on the fringe, including those that are very technical and deep scientists within this field, that they argue that perhaps maybe those in this particular space are making a bigger deal than it needs to be. In the sense that they believe that there are adequate data and technologies, existing technologies, to help satellites maneuver away from debris, keeping in mind that when we think about space, even in LEO, it's a lot larger than people believe. Some say that satellite manufacturers are also designing systems to deorbit on their own. So there really isn't a need for this space debris removal solution. How would you respond to some of them?
So the first thing is that when it comes to data, it's a little like saying we just need better data on ways about where broken cars are. We don't need tow trucks to remove cars from motorways. Well, one thing is that it might seem that LEO is a big environment, but what happens is that the number of orbits that are really valuable are discrete, right? We already see that constellations don't launch between 600 and 1,000 kilometers. Why? Because they can't. Right, they can't take the risk for operation is too high in those orbits, and some of the orbits we already see Kessler syndromes appearing. So we have more between 700 and 900 kilometers. The number of objects increases over time without fundamentally new satellites being launched in this area. So the problem is obvious. The question is who's going to buy this first, right? What is the adoption curve? There is a lot, and there's a mix-up, I think, between argumentation used by a satellite operator to achieve license, to obtain licenses, and the tendency is to minimize the issue and the problem, and the reality of the environment, right? The reality of the environment is that it is not a sustainable environment. It's just not. The fact that we have no way to clear up objects that orbit at 28,000 kilometers per hour above 600 kilometers in a reasonable time frame is by definition an unstable environment. So today what we see is that the first people that really pull the alarm and raise flags and say we have to do something about it are agencies, and typically agency operating larger satellites, right? So ESA is paying a lot of money into this, and the reason why they do that is because they see that this is not just not viable on the long term, and they need to protect their assets, and they need to create an environment that can be operated in the future by all the constellations that are going to be launched up there. So we see this changing rapidly. It's really interesting. When I started ClearSpace at the beginning, the first in 2018, 17, 18, I was going to conference. Everybody was saying, we need better data. We just need better data. We avoid objects. We need better data. And as years passed by and we continued working on our project, every single conference, the subject was evolving, and you could see the space debris subject is a constant element of every single conference. And in the latest year, everybody says we have to remove stuff. We are in a situation where this is not sustainable and they have to be addressed. The other element about having self-deorbiting capabilities, most satellites do already, right? And they do for years, right? The satellites developed in 2010, 2015, 2020. Certainly, every large platform has a propellant budget to deorbit. So the need there is this capability is there for a long time already, and it's sort of like assuming that cars never fail, right? You need a servicing capability for cars because they do fail, because otherwise they become just way too expensive to operate. What we see in terms of activation of initial needs from operator is the fact that you can reallocate your fuel for operation if you can count for with the orbit and service. So one of the important first commercial conversations we have with operators tend to be with operators that have large platforms and allocations of fuel. So I'll give you an example. You've got a meteorological satellite, it's got a 5-year span in orbit and costs 500 million. And there's a few of those, right? This satellite, because it's a 3-ton platform, needs to do a controlled reentry, because otherwise it might end up cutting the air traffic over Spain on reentry, like what we've seen last year with Chinese rocket body, where we start having serious risk on air traffic or other infrastructures on the ground. And so those operators know they have to do a controlled reentry. If they can reallocate their reentry fuel onto a maintaining operation, they can delay their investment for a period of 5 years, or even in some cases, 10 years. So if you calculate the 500 million investment for 5 years that you can extend to 10 years, you can very rapidly calculate the return on investment on the deorbiting operation. So the first places where we see a real interest, a commercial interest, is that kind of operation. Then the other one are large objects. Quite a few of them are large objects. The question is, how will this evolve over time? How does a new industry like a servicing or deorbiting industry evolve over time? Right? And that's really the question. I hope it was a long answer. I'm sorry for that, but I hope that kind of covered the complete span of the question itself.
Thank you. I appreciate that. And again, it was I think somewhat of a rhetorical question, because I think everybody agrees that it's a serious problem. It needs to be addressed. Now, when we think about space debris removal, it's a lot more complex and diverse. Right. So it's not just larger objects, it's fine debris that's going at incredible speeds. So talk to us about how your design of that 4-arm capture system for its robotic satellite, how that differs from some of the other solutions or proposed solutions that are out there, like nets and laser blasts and harpoons, giant foam balls and puffs of air, tethers to solar cells, and anything in between.
Yeah, so there's a question. There's multiple trade-offs we had to do at the beginning of our work, right? And our approach was not we were not trying to push a technology. We were asking what is the right way to address a specific problem. So to give you some context, the first question we look at the space environment. You can look at it like an environment where you've got sources of small debris and sinks of small debris. Sources are fragmentation events of larger objects, right? So the source, what generates a lot of those small, tiny, thinner debris are fragmentation event, batteries, explosion, it can be collisions. So it's really larger object that generates small debris. The sink, there's only one, is atmospheric drag, right? So in this environment, what we are missing, and in particular in specific altitudes, is an artificial sink, right? And then the question is, where do you start? And our take was, we rather start with the source than start with the small debris. And the reason is because there's a saying, I would fix the fence, but I'm too occupied chasing the chicken, right? So the idea for us is, how do we fix the fence? That's how we started. The other question was, okay, find what technology to grapple a large object. So you can go for a harpoon, and we traded this off because we just don't believe it's a good idea to throw a harpoon against a satellite that carries hydrazine, right? So the risk for the operation is high. The other weakness of a harpoon is that it's a single-use item. So you shoot one harpoon and then it's out there, and then you have to shoot another one, right? So every time you add another element into your equation of capture, you make it more complex. The net has the same problem of single-use solution. It's got two problems. The first one, why we traded off the net, was that if you miss, then you have to capture a satellite in the net. The second one is that you end up, if you succeed in the capture, you end up with a two-body system that is tied by a rope. And in space, a tether is really hard to manage. It's extremely hard to manage in terms of navigation. And in the worst case, you might end up in a spin of the two object, which is a system that you cannot stabilize anymore. Then the other element that we brought in is we have to be able to repeat operation. It is a really difficult thing to pick up. It's like providing roadside service to a car that orbits at 28,000 kilometers per hour in the void of space, without friction and without gravity. Everything floats around. So any contact with the object generates spin, motions that you don't want, generates complexity. So doing the capture is difficult, and you have to be able to repeat operation if you fail. You have to also be able to repeat operation if you want to do a reusable platform. So that's all the drivers that led us to the solution we have today. The last trade-off we did was, another one is the orbiting kit, right? There was a discussion, would the orbiting kit be a solution? And our take was no, because you have to sell the orbiting kit 3 years before the mission flies for all the satellites, even the ones that don't fail, right? To an operator, to a system integrator. And then you have to use it. The value you produce out of the system happens 3, 4, 5 years into the mission, right? So this is an extremely difficult sale and business case to make. And then it's the additional weight, mass over the complete constellation can be massive. So we came to a conclusion that it's like adding a car to a car, right? You have to be able to navigate. You have to be able to vector your thrust to be able to navigate back into Earth's atmosphere. You have to have an avionic on board of the orbiting kit. So you need propulsion of the orbiting kit. You need power. So once you put all those elements together, you realize, okay, this equation is really hard to make. And the last one was, is docking plate a good solution? And the answer is yes, it is. The docking plate is a great solution. Problem is, the first customers don't have docking plates. They just don't. The first customer where we sell missions and the first contract for mission we sign doesn't have a docking plate. And when we looked at it, we came to the conclusion that the pioneers and early adopter in your adoption curve don't have a docking interface. So for us, the docking interface is simplification. We can buy a docking interface. We can develop the magnetic docking system or whatever grappling system for docking interface relatively easily from our initial development process. So this is what drove our selection of how we approach the problem. Then the last point that really differentiates us from the other solutions in the market is that we raised 30 million at this stage, and we already have 2 mission contracts on the table. Who else does that?
Yeah. So I think alluding to what you're saying is that there's still quite a complexity. So even with the best case solution that you guys have come up with, the reality is getting close enough to that target satellite in just the right speed, at just the right altitude, just the right angle. And again, keep in mind, I mean, for all purposes, you have to basically be almost touching it before you can actually start to grab it and pull it in. Talk to us about some of the hardware as well as the algorithms that are being used and being optimized to help fine-tune that final capture process.
So yeah, that's a very good point. And by the way, it speaks to your previous panel on launch capability. We have to do a rendezvous, and we have to do a rendezvous of a satellite of a servicer that's probably in the 700 kilogram range, which means that all the small launches of 300 kilogram just don't fit for our need. And the larger one might not get us to the right orbit, right? Because they will be driven by other requirements than ours. So there's a class of launchers that 1 ton, 2, really interesting. This said, in terms of technology, obviously we have to do first a rendezvous, and that's very known. I mean, the Dragon capsule does that a lot. ATV in Europe did that a lot. I mean, this is Soyuz that do that. So navigation to get to the right place and to the right orbit is something that is done and experienced, and there's a lot of experience with that. When we get to close proximity, there's multiple dimensions of the problem. The first one is a guidance, navigation, and control problem, where we have substantial experience on board. Our lead of guidance, navigation, control has flown 3 mission information flight and wrote numerous amount of the background IP and know-how on angle-only navigation and how you get with the minimum number of sensors close to your target. The big challenge is to do the capture itself, right? So we worked, the first element that you need, which is a key technology element, is the navigation system, which is the capacity out of a relatively simple sensor to get a very clear understanding what the motion, movements, proximity, distance, relative velocity, rotation rates of the targets are once you're at proximity. And so we did a substantial amount of work there and are very mature on those technology. Then the next step is you have to do path planning for the capture. You want to optimize the capture angle, specifically if you have an object that has solar wings on it. So you want to be able to do that and then do robust control. And the robotics of the capture system is another element. You want to be able to capture the object before you touch it. And the reason why you want to do that is if you touch it before you capture, you affect the system, which makes it more difficult to capture. So the choices we make are really focused around this capture without touch and then securing the object. Once this is done, the next problem you have to solve is that you need to recalibrate your center of mass so that you can actually fire a propulsion system in a direction that is not a rotation. And that's another dimension of the problem. And then the rest is navigation. Right, so those are the key elements of the problem. Now, what we have as an opportunity on the ClearSpace One mission is to solve all those problems on a real case, right? And once you tackle the center masterpiece of capture, picking up something, navigating a stack, then you're in a position you can provide any other service. So this is really the masterpiece you want to control, to be able to master in-orbit servicing. And all of them are present on ClearSpace One. All of them will be present multiple times on ClearSpace 2, and will be present for a cooperative target in the case of a geostationary satellite 2 times in the ClearSpace 3 mission.
Great, thank you for that overview. Let's talk a little bit about business opportunities in the sense of going beyond ESA grants and sponsorship. So right now, yes, the bulk of the revenue is coming from the ESA contract, right? And certainly in the US, NASA, of course, is a big customer of many of the space-related companies. But talk to us about, after kind of that 2028 and beyond, who are the private commercial payers and why would they be paying, and what is the specific context of why they would pay? And putting a caveat that when Starship comes into play, certainly on the LEO side, some of those satellite operators may not necessarily want to refuel or service, but rather just let it decommission or just go out of connection, right? GEO is a different matter. So help us trying to understand the different revenue sources and how you can really commercialize it from the private side.
Yeah, so I think first of all, our take is that the first commercial customer is customer where we don't co-fund, where we have a profit on a mission, will likely be of the institutional defense type, right? Those are actors that have large platforms in orbit, which have been quite expensive, and where they can do fuel reallocation. That's the first target, what I mentioned before, the fact that you can extend the life and the operation. It's not really about the orbiting itself. It's about using an external deorbiting service to extend life of an expensive sensor in orbit. So we expect those are typically the first one that will sign up for paid contract where there's going to be a fully paid service, right? From there, I think when we look at the constellation segment, the lower orbit constellation, like, for example, SpaceX, and probably at least at the beginning, Amazon Kuiper, they're not going to be an early adopter. If they're anything, they're lagger, right? Or a late adopter. Mostly because they're low enough. They're below 550. They come back into Earth's atmosphere within 5 years, right? And the FCC regulation pushing down from 25 to 5 years, they're still in. So they don't really need to care so much about that. I think they will face another problem is that a lot of those platforms that will drifting back down will go through ISS orbits and space stations orbit. And that's going to be one of the challenges that will have to be overcome. But today, we just don't see the business case there yet, right? We will have to bring down the cost of a servicing substantially low, right? You have to be in the realm of 1 million per deorbiting if that's the service model. Where we can see as high level or high level altitude or the constellation, it's a different story. And they might be interested into an insurance service, right? Into more like a AAA kind of service where it's a subscription that essentially takes over the liabilities for the orbiting to be able to obtain extension of life of a 6 billion investment into a constellation for the launching state, right? Because they'll say, I've got a 5 years nominal lifetime. I want to extend 2, 3, or 4 years. Everything still works, right? And put on the table a guarantee for the launching state saying, well, we want to extend and to give the guarantee that the failures will be deorbited because those ones remain for close to 1,000 years or more in orbit. We will insure this risk, right? And this, at some point, we were thinking maybe ClearSpace should be an insurance company, not a deorbiting company. The question is, the technology is really an enabler for a financial transaction, right? And so we looked at it this way. So we expect that very likely is going to be how this kind of services for deorbiting might materialize on short term. That's what we see on the horizon. Geostationary is a very different business case, much more simple, much more straightforward, where essentially you extend the life by taking over the station keeping of an expensive satellite for another 5 years. And there the market is already mature. We already have a very advanced discussion with multiple operators on this subject, and we have term sheets signed for that kind of services.
Now, I know we're out of time, but I have to ask, which is talking more longer term. Again, I don't know if it's 10 or 20 years, but what's the architecture or infrastructure, I should say, that we can envision in space, recognizing that you may potentially need a fleet and an actual station in space to be able to actually not only grab, but also, process, I think repairs and so forth.
Exactly. This is really, if you want, the ideal solution is if you don't need to actually deorbit. Right. If you can find ways to reprocess the architecture in orbit, there's another dimension. So we expect there's going to be fleets in the future of that. And the approach will be quite similar. There's going to be additional services for operators in orbit, which means that the inclination and type of orbits that the operator might choose might just be because in this specific orbit and inclination, it's going to be cheaper to operate because you have additional services available already. So we expect that this will very likely over time materialize. What we expect also is that in-orbit servicing might change the equation of how you design a satellite, because you can make very different choices when you don't care so much if the satellite fails, whatever the altitude, right? So it's fine. It can fail. It's no problem. So this will drive a lot of the choices in the development. We see already institutional actors, at least in Europe, starting to put docking interfaces on the large scale satellites on purpose because they say, well, I've got this is going to be an option. For us, the fact that we have, and just a parenthesis here, the fact that we have an ESA mission and that we will fly with ESA essentially gives us a rubber stamp from ESA. This means that to be able to intervene on a Copernicus satellite or in a EUMETSAT satellite, we will have all the credits to do that, right? So we'll be in a very unique position to do that kind of services, which is likely going to be some of the earliest ones. Now, in the long term, recycling in orbit, having interfacing with space stations makes a lot of sense, and we already have discussions in that sense with different actors working in this field. I think the future is going to be an environment which kind of will stabilize in something that makes optimum sense, where you don't have just a cost reliability curve in space, but also the maintenance cost curve that will allow to just bring the complete space industry into new optimum. And this is really what we're after.
Great. So we are out of time. I want to thank Luc for a terrific conversation on space debris removal and satellite servicing. Please give him a round of applause. We transition to our AI, robotics, and autonomy track.
Thank you very much.